Excellent. Okay, so we've talked about the idea of approximating area under a curve using Riemann sums. And so we have three different ways that we can do that. We've talked about left Riemann sums, right Riemann sums, and midpoint Riemann sums. Another idea that we talked about before but haven't actually put into use is the idea of using trapezoids instead of rectangles like we would in a Riemann sum. So just to review, if I'm using a trapezoid, do you guys remember what the formula for area of a trapezoid is? So the area of a trapezoid is 1/2 the sum of the bases, base 1 plus base 2, times the height of the trapezoid. Do you guys know how to identify what the bases and the height are in a trapezoid? Bases are the sides that are parallel because a trapezoid has two parallel sides, and the height is distance between the bases. That's a good way of thinking about it, or just the length of the segment perpendicular to the bases, right? So our trapezoids are actually going to be right trapezoids. We'll look at why that is in a minute. But we have other ways of drawing trapezoids. We have isosceles trapezoids and stuff like that. Right trapezoid just means that one of the sides is perpendicular to the bases. So the parallel sides will be our bases, and it doesn't matter which one you call base 1 or base 2. We're going to add them together in addition's commutative. The height is the distance between the bases, or the length that is perpendicular to the bases. So this would be our height. And the reason that we might want to use trapezoids as opposed to a Riemann sum is because if we have some kind of curve and we partition it into different parts. We said rectangles don't always fit the curve as well as other shapes. So if we use a trapezoid instead of a rectangle, then we're starting to fit that curve a little bit better. And so we're coming up with approximations that might be a little bit more accurate. So we're going to use some different methods to estimate the integral from 5 to 14 of f of x with respect to x, given this table about our function values. So they've given us our function at various x values, and we're going to use that to approximate the integral from 5 to 14 f of x dx. First using a left Riemann sum, then we'll do it with a right Riemann sum, and then we'll check out what a trapezoidal sum would look like. So I'm going to use 3 subintervals. There's only one way I could do 3 subintervals. My first one will be from 5 to 8. My next one will be from 8 to 12. My last one will be from 12 to 14. If I'm going from 5 to 8, that's going to be a partition width of 3. From 8 to 12 will be a partition width of 4. And then from 12 to 14, my last partition will have a width of 2. So if I'm using a left Riemann sum, I'm doing the area of a rectangle. Its base will be the width of the partition. So for my first partition, the base has a width of 3. And the height of my rectangle will be the left endpoint's function value. So 6. My next partition from 8 to 12 would have a width, a base of 4, and a height equal to the left function value, 10. And then finally, my last partition has a width of 2 and a height equal to the function value of the left endpoint, which would be 9. 3 times 6 gives me 18. 4 times 10 gives me 40. 2 times 9 gives me 18. So 76, right? 36 and 40. So my left Riemann sum approximation of that definite integral would be 46. What if we had done that approximation using a right Riemann sum. Well, I'm still using the same partition, so I still have the same partition width, but this time for each partition, I'm going to use the function value at the right side of the interval. So my first partition, it still has a width of 3, but now its height will be the right function value, 10. My next partition still has a width of 4, but its height now will be the right side function value, 9. And then my last partition has a width of 2 and a height equal to the right function value, 17. So we've got 30 plus 36 plus 34. So that would be 70 plus 30, 14,100. Close. Something between 1 and 1,000. You know. It's an approximation. There's margin of error. So what if we did a trapezoidal sum? So now instead of finding the area for these regions using rectangles, we're going to find the area of each partition using a trapezoid. Again, we're approximating the integral from 5 to 14 of f of x dx. So going back up here to my picture, if I were looking at just one of the partitions there, thinking about what we said up here about the bases and the height, what would the bases of that trapezoid be? F of x where? The function value at the beginning of my partition and the function value at the end of my partition. So now the left and right function values represent the bases of the trapezoid, whereas before they represented the height of the rectangle. What would the height of my trapezoid be? The change in x, the distance between the two. So the width of the partition, which was the base of the rectangle, now represents the height of my trapezoid. Do y'all see that? So for my first partition, if I approximated the area from 5 to 8 using a trapezoid, I'd have 1/2. Base 1 would be my left function value, 6, plus base 2 would be my right function value, 10, times the height would be the width of the partition, 3. Plus, my next partition, its area would be 1/2. My base 1 would be 10, the function value of the left endpoint. My base 2 would be 9, the function value at the right side of my partition. The height would be the width of the partition, which is 4. And for my third partition, its area would be 1/2 base 1, which would be the left side, 9, plus base 2 is my right side function value, 17, times the height is the width of the partition, 2. So let's see, we've got 16 divided by 2 would be 8, times 3 is 24. I could reduce that 1/2 and a 4 to 2. So then I have 10 plus 9 is 19, times 2 would be 38. And then here the 1/2 and 2 cancel out completely. So we'd have 9 plus 17, which would be 26. So that would be 50 plus 38 would give me 88. Oh, I'm off the screen there. So let me ask you guys, what would the advantage of using method A or method B as opposed to method C be? What do you mean by time? Calculations are a little bit easier and therefore faster, right? It's a whole lot easier to multiply base times height than it is to multiply 1/2 times base 1 plus base 2 times the height. What do you think the advantage of method C is? more accurate, right? And that was an idea that we talked about when we first started talking about approximating area under a curve. Before I even told you guys there's a trapezoidal rule, you said, well, what if we did it like this, if we fit the curve better? Well, yeah, it fits the curve better. Absolutely right. But a little bit more time consuming because the calculations are a little bit more involved. Do you guys have any questions about left, right, or trapezoidal sum? Okay. Let's look at the next one. This is an application of those approximations. Water is flowing into a tank over a 24-hour period. The rate at which water is flowing into the tank at various times is measured, and the results are given in the table below, where RFT is measured in gallons per hour and T is measured in hours. The tank contains 150 gallons of water at time 0. So this time they've given us a table with different times from 0 to 24 hours, and they've given us the rate of change of the water in the tank, the rate at which water is flowing into the tank. So they want us to do two things, well, really three, the same thing, but three different ways. They want us to estimate the gallons of water in the tank at the end of 24 hours. First, they want us to do that with a midpoint Riemann sum. Then they want us to do that with a trapezoidal sum. And then at the end, they've actually given us an equation to represent that rate. And they want us to find the actual amount of change and use that to find the actual volume of water in the tank. So if they have given me the rate of change, how can I use that to figure out the volume in the tank? Integrate it. What do you mean by integrate? Can you be more specific? Let me get my words right. You're not wrong. I'm just asking you to be more specific because we talked about integration a lot of ways. First off, how am I going to integrate a table? So, all right, so if I multiply gallons times hours, I'll get gallons. You're right. And that's going to happen somewhere in my process. We talked about that idea before. What would I need to do with the rate of change to figure out the volume? Okay. And how am I going to do that? What's the relationship between rate of change and... Well, there's a hint. They want us to estimate using a midpoint Riemann sum. What is the midpoint Riemann sum calculating? Area under the curve. What does the area under the curve for rate of change tell me? The amount of change. So if I can use a Riemann sum or a trapezoidal sum to approximate the amount of change, and I know how much water was in when I started, I can use the amount of change and how much water was in the tank when I started to find how much is in it at the end, right? What about in part C? They haven't asked me to do a trapezoidal or a Riemann sum. Instead, they gave me the equation of a function. Can you be more specific than integrate it? They want me to... You're being less specific. They do want us to find something. They want us to evaluate a definite integral. If we take the definite integral from 0 to 24 of that function, we are finding the area under the curve of that function. And the area under the curve of the rate of change is going to be the amount of change. You can also think of it as the fundamental theorem. If I take the definite integral from 0 to 24, that's going to be equal to the volume in the tank at time 24 minus the volume in the tank at time 0. And that difference is the amount of change. So I'm going to give you guys a little bit of time to work on that and see what you can come up with. By the way, you can use your calculators on this if you want to. So when you get to this part, you could evaluate the antiderivative by hand. Use your calculator for practice. You could do it with the 84 or the 89.